second day. Yeah, that's right. Okay. So Alex is going to tell us about perfect zero knowledge for quantum multiprover interactive proofs. And this is joint work with William Slofstra and Henry Yuen.
So thanks for coming here early in the morning. So let me introduce, and the topic of my talk, like quantum zero knowledge, it lies in the intersection of three different fields, and of quantum foundations, cryptography, and TCS. And because of that, I will start slowly and recall everyone what are interactive proof systems. So everything in this room should remember what NP is. So we have an unbounded prover that helps, that is untrusted and try to help some bounded verifier to decide some language. And require that if the string is in the language, then there is a message that the prover can send to the verifier that makes her accept. But if the string is not in the language, no matter what the prover sends to the verifier, she should reject. But then we can start thinking, why should we have just one-way communication? Why can't the verifier also ask questions back and challenge the prover? And with this, you can define the complexity class IP with the same set of properties. We want that for yes instances, there is a strategy for the prover that makes the verifier accept. And for no instances, no matter what the prover answers, the verifier should reject with high probability. And again, we can ask ourselves, why limiting ourselves to a single prover? And we can go to the multiprover setting, as Anand introduced yesterday. And in this setting, we have two provers that in an offline phase, they share some strategy. But when the game starts, they stop interacting, so they don't communicate. And we're interested like in protocols where for yes instances, there is some classical strategy that the provers share that makes the verifier accept with high probability. And if the string is not in the language, no matter what these two non-communicating provers do, the verifier should reject with high probability. So multiprover interactive proof systems in general, they're very useful in complexity theory, but for cryptography, there are some extra properties that would require. And one of them is zero knowledge. And we know that adding power to these proof systems actually increases expectedly increases the computational power. And I was saying, one extra property that we would like from our interactive proof systems for cryptography is zero knowledge. And intuitively, this says that after interacting with the provers, the verifier learns nothing that she could not cook up herself. How do we define this? So first, we're considering malicious verifiers. So because we want to be paranoid and think that the verifier could deviate from the protocol to learn as much as she can from communicating with the provers. And after communicating with her, she has some output that's here described by this random variable x. And we say that the protocol is zero knowledge if you can actually have some simulator that's polynomially bounded and does not talk to the provers and output some random variable y. And we say that this protocol is perfect zero knowledge if the distribution of the output of the original protocol and the distribution of the output of this bounded simulator that does not interact with provers is exactly the same. Okay? And as counterintuitive as it seems, we can actually show that every language in MIP, so every language that can be proved by multiprover interactive proof systems, can be made zero knowledge. And this result was fundamental in order to develop zero knowledge for cryptographic settings. And what quantum computer science like to do is put quantum in front of every possible world. So we can define every proof system that we had before. We can consider its quantum counterpart. So let me focus only on the multiprover setting. So now we have quantum provers that share a quantum strategy. And they communicate, let's say, with a quantum verifier that and at the end of the protocol, this verifier should accept or reject. And now, what we want for completeness is that there is a quantum strategy for the provers that makes the verifier accept. And for no instance, no matter what quantum strategy they have, this quantum verifier should reject. But very interestingly, Reichert, Unger, and Vazirani, they showed that actually in this model, you can consider only classical verifiers. So a classical verifier can just delegate the quantum power to all the provers and decide all languages in QMIP. And this complexity class is called MIP star, and we learned a lot about them yesterday. In particular, we know that in this multiprover setting, we can even solve double exponential, non-deterministic double exponential time. And as in the classical case, we can also consider what happens if we require that the verifier learns nothing from the interaction. What happens if we want to use such protocols for cryptography? And not surprisingly, we can define the same type of requirements. We want that this malicious verifier that outputs some random variable x, and you say that is zero knowledge if there is some simulator that might depend on this verifier and output some value that has some distribution that's described by this random variable y. And we say that this protocol is quantum zero knowledge, again, if the distribution of these two variables are exactly the same. And here, I'm assuming that this verifier and this simulator are classical for simplicity, but we could also study the case where they're both quantum, but without loss of generality, I'm assuming that they are classical here. So Chiesa et al., they proved last year that MIP is contained in perfect zero knowledge MIP star. So we know that perfect zero knowledge MIP star is at least as powerful as perfect zero knowledge MIP. But the main question after that is, what's the characterization of this complexity class? Can you show that it's equal MIP star? And that's exactly what we show in our result. We show that also multi-proof interactive proof systems with entangled provers, they don't lose computational power if you, on top of that, require perfect zero knowledge. And for the rest of my talk, so in particular, this implies that everything that can be solved in non-deterministic double exponential time can be solved in perfect zero knowledge. And for the rest of my talk, I'll first describe the simulatable codes, and this is the main tool that we use to prove our zero knowledge protocol. Following by describing this compression scheme defined by Fitzsimmons et al. And finally, I'll show how to make our zero knowledge protocol based on these two tools, these two technical tools that we have. So instead of defining formally simulatable codes, I'll try to explain it by example what their properties are. And here we can pick an example of the STEAM code. And this is a quantum error correcting code, so we don't need the details, but the idea is that you map 1 qubit into 7 qubits. So the if the state is 0, this is mapped to this big state. And if this qubit 1, it's mapped to this orthogonal 7 qubit state. And quantum error correcting codes, they're very important in quantum computation because when quantum computers will be there, they're noisy, so they're very important in order to perform actual quantum computation. So given some 1 qubit state psi, we can try to analyze we can analyze the encoding of psi under the STEAM code. And in particular, there is one question that I can try to say is, what happens if you, instead of looking to the whole code word, that you look just to parts of it? So what happens if you just, for instance, look to these 2 qubits? And from a not very hard calculation, we can see that no matter which 2 qubits you look at in the STEAM code, this value is totally mixed. So these are just 2 random coins. So in particular, there is a very efficient algorithm that given a subset of 2 qubits of the STIN code, output what's the reduced density matrix on these 2 qubits without knowing the state psi. In particular, this algorithm outputs identity. Okay, so it's a very efficient algorithm. And then we can go and we can ask, can we go further? Can you look to the reduced density matrix on 3 qubits instead of 2? And we cannot. And it's easy to see if you look to the encoding of 0 and 1, and you see that when you look to 3 qubits, you can distinguish them both. So without knowing what's the logical qubit that's being encoded, you don't have this oblivious way of outputting reduced density matrices. Okay. So the main question is, can we, for every parameter S that we have, find some error correcting code such that we can compute the reduced density matrix on at most S qubits of every code word without knowing the encoded data? And the answer is yes, and the idea is just repeat encoding again. So before, we had this encoding of some state psi, but we can go to a second level where every physical qubit of your encoding is encoded again with the STIN code. So now your physical qubits, so you have 49 physical qubits that are the encoding of your state psi. And now, if you look to these 3 qubits here, they're not totally mixed, as we saw before, but they are an encoding of a the totally mixed state of a qubit whose value is the totally mixed state. So because of that, no matter what psi is, the reduced density matrix on these 3 qubits are fixed. And in particular, you can efficiently find its value and output what it is. So more general, what to show is that, okay, if you want to compute the reduced density matrix on S qubits, you can pick a large enough, like you can concatenate the STIN code with itself for enough times, and then the reduced density matrix will be efficiently computed. So quantum error correcting codes are very good to encode data, but we can also do much more with them. In particular, we can compute on encoded data. And we want our simulatable codes to somehow also be useful in the setting. So for instance, some set of quantum operations that can be done transversally. What do I mean by that? Is that if you have some encoding of some quantum state, and you apply some quantum gate on every qubit of this encoding, this is equivalent of applying this quantum gate on the logical level. And what we'd like to do is, in simulatable codes, is not only be able to simulate reduced density matrix on code words, but also be able to compute the reduced density matrix on the snapshots of the computation. So at every step of the computation, you can compute the reduced density matrix of that ongoing code or ongoing computation. And it's not very hard to see from our previous step that this can also be done efficiently if your code is simulatable, if the code words are simulatable themselves. So this is the right way to go, but we know that not all quantum gates can be applied transversally for every quantum error correcting code. And to bypass this, we can use more tools from fault-tolerant quantum computation. In particular, we can have gadgets of computation by teleportation in order to perform computation. So for instance, there is this T-gate that cannot be applied transversally with a STIN code, but if you're given some resource state called a T-magic state, you can apply only applying operations that can be implemented transversally. You indeed can apply the T-gate on your target qubit. But so, in particular, we could consider the encoding of this qubit, the encoding of the magic state, and the output should be the encoding of the T-gate applied on your qubit. So it should be easy from our previous result. But not really, because here we have some measurement. And when you have to do a measurement and decode it to perform this correction, this is not clear to be simulatable. Luckily, the outcome of this measurement is very well behaved, so in particular is the totally mixed state. And then the proof is very technical to keep track of what are the state of every encoded qubit, but what we show in our results is that we can indeed simulate even computation on this set, on this, using these gadgets for computing T gates. So this is the overview of what simulatable codes are, and now we switch gears to our second tool, and these are the compression schemes of Fitzsimmons et al. And when you look into MIP star protocol, you can see it in a different way. You can see it as a circuit. And in this circuit, the verifier, that's polynomially bounded, she performs first some polynomial time computation. Then she sends some message to each prover, who then, the provers, they can apply whatever unitary they want, so an exponential time unitary if they want, and then they answer back to the verifier, who then decides to accept or reject. So I'm just writing a protocol as a quantum circuit. And what Fitzsimmons et al., they realized that you can somehow encode the computation of this computation in what we call the generalized history state. And this is the superposition for every time step of the computation. So for every time t, we have in this superposition the first t gates of your computation applied on the input state, where these gates are either the verifier gates that we are a bit more fine-grained and we can pick every 2-qubit gate that the verifier performs, or we are more relaxed and you say whenever it's a prover operation, we let him do whatever he wants. We let them do whatever they want. And what Fitzsimmons and all, they showed that there is an MIP star protocol that tests generalized history states. That's not very surprising because we start with MIP star protocol, so we went with MIP star protocols. But in these new MIP star protocols, they have different properties, but here's, it's not the focus of my talk, so I won't have any comment on that. What I'll comment is how they perform this protocol. And the idea is that the provers, so they have multiple provers in their protocol, and they should share an encoding of this history state. And the verifier asks the provers to measure some parts of this maybe exponential size history state. And this problem is far from being zero knowledge because the verifier could cheat and ask the prover to measure correlations that she should not be allowed to know. So in our result, in our protocol, what we do is, starting from this circuit that represents the MIP star protocol, we can consider the encoded version. We can consider that the provers, they share the encoding of their quantum state. The verifier performs the encoding of the auxiliary qubits, and then perform the computation either transversally for Hadamard's and Clifford's, or using magic states with the gadgets that we saw. And at the end of the protocol, the verifier has the encoded output, and then she just needs to decode it and output 0 or 1. And it's not hard to see that if the maximum acceptance probability here is some parameter delta, the maximum acceptance probability here is still delta. And what we show is that if we consider the compressed protocol when this encoding is under a simulatable code, then actually this compressed protocol is a zero knowledge protocol. So from our results, there are some follow-up questions. The first of them, can you have more applications of simulatable codes in quantum cryptography or quantum complexity theory in general? Secondly, we can give more resources to the provers. So for instance, we can assume that the provers can do an arbitrary computation that does not violate, that information was transmitted faster than the speed of light. And you can ask, does require zero knowledge for this complexity class lose its computational power, or is it equivalent to them? And finally, as you saw the talk by Anand yesterday, we really don't know an upper bound to MIP star. So can you use this new characterization of perfect zero knowledge MIP star in order to put an upper bound to it? And I think I have 1 more minute, so I'll answer the first question. So we indeed found some more applications to simulatable codes. In particular, showed that this problem of consistency of local density matrices is QMA hard under cap reductions. And it seems very technical, but like the idea is that this problem was shown to be QMA hard under 2 reductions, and it has been an open problem for 13 years. So using this, this framework with n broadband, we can show that it's also QMA hard. And for that, we can have more efficient zero knowledge protocols for QMA, and making them closer to practice in the sense that, okay, we can have more applications that use zero knowledge protocols as basic tools. And thank you for attention, and I hope the talk is not zero knowledge.
Yes, I have 2 questions.
Uh-huh.
When you showed how to make IP store, you had 7 provers. How do you get up to 2?
Oh, sorry, we don't get. We still have 4. We have 4. We have 4.
And my other question is,
I will say, I think.
so does this technique allow you to complete bypass markers winding technique? They are somewhere in there.
No, the point is we don't need to use it because the provers don't have to commit to anything. They don't have to guess. The point is you can compute the reduced density matrix. So whenever they receive the questions from the verifier, the simulator can actually compute this reduced density matrix and answer exactly what it should be.
That's what I meant by bypass. So you do bypass.
I will do bypass then. Yeah, okay.
Very good.
So, do I? Mm-hmm.